this is Mrs. Murdoch, and I am going to talk today about how to do those U-shaped tube problems that you sometimes encounter in this unit about cell transport. So you may remember Mr. Anderson in one of his videos showed a situation where you had a U-shaped tube, literally a U-shaped tube that has two sides to it. So that down here there's this semi-permeable membrane, usually a a man-made membrane, which semi-permeable, which obviously can let some things in through and some things it can't let through. And it's kind of like the dialysis tubing that we talked about. So being man-made, it just has to do with how big the pores are in it, right? This is very different from real life cell membranes that are in our bodies and in the living things. A cell membrane can be much more selective and much more active or passive about what it lets through because it's a biphospholipid bilayer with active proteins that change shape and can let things through or not let things through, whether they're present or not. A man-made semi-permeable membrane is just a piece of plastic with holes in it. So it's much less versatile and adaptable than real membranes. Nevertheless, we have these U-shaped tube problems which give us practice in terms of what kinds of things can diffuse through it and what kinds of situations will cause that diffusion. So usually when you're given a problem like this, you are told what the semi-permeable membrane can and can't let through it. In this case, let's say that water can go through, but the sugar dots on either side cannot go through. So in this situation, let's say that there's more sugar over here on this side than there is on this side. And as a result of that, what's going to happen? Well, the sugar can't move, and no situation in nature likes to be unbalanced like this. So the only way for this situation to equilibrate would be for the water to move. And the water, remember, is the white space between the dots. So the water will move towards the solution that's more concentrated in order to dilute it, right? That will, and since the sugar can't move in the other direction to help, that will push the water in this side B up, and then the side A, water will go down until both solutions have the same concentration. Okay? So that's what would happen in that situation. The water would go towards side B. Side B water level would go up. And it's all about reaching equilibrium. In every problem like this, usually they say, well, here's a situation at the beginning of an hour. Tell me what the situation will look like at the end of an hour. And in this particular simple example, you would say, oh, well, side B water level would go up because the water is moving towards the concentration that's greater. Water will always move towards where there's more solutes. But in terms of water itself, remember that water will always move from where it's higher in concentration to where it's lower. So from the water's perspective, this is still true here. From the water's perspective, it's higher in concentration over here, right? Because there's fewer solutes. And then on this right side, it's lower in concentration here because there's more solutes taking up the space. So you're still following the law of diffusion. Water is flowing down its gradient. Okay, so then often they'll change the situation. What if they said, okay, now the sugar can move. Now the sugar can move, so now this might change the situation. Let's think about that for a minute. So now if the sugar can move, and so can the water, right? They both can move. Now what will happen? Well, now, since the sugar can move, it will. So these dots will start to diffuse this way, right? Until the concentrations are the same on both sides, right? So the water then doesn't have to move so much to help equilibrate both sides. And what will happen as a result of that is the water levels don't need to change because the solute will do the equilibrating and the water doesn't really need to help. Okay, now let's try a more complicated problem. This is another problem that I think might be in your in your worksheet that I gave you. So now we have more than one solute to deal with. And the other thing is that it will tell you, well, in this case, the monosaccharides, which are smaller sugars, right? The monosaccharides can move, but the disaccharides cannot. Okay, the disaccharides cannot move, right? All right, so that tests your knowledge a little bit. Go back to biochemistry. We know that which one of these is a disaccharide? Can you tell me? The sucrose is the disaccharide, so the sucrose cannot move. But the fructose is a monosaccharide. It can move, and so can the glucose. So here's what you need to know, and this is a funny thing about these diffusion problems. Each solute, right? Each solute, assuming it can move, will move independently, okay? Independently of other solutes to reach equilibrium on either side of a membrane. Okay, and what that means in English is that the fructose will, since there's more over here and there's none over here, the fructose will just move this way until it is completely equal on both sides, so that over here you would eventually have 0.1 molar fructose. So you would divide this 0.2 in half so that it would move until it was 0.1 and 0.1 on both sides, right? The glucose is going to do the same thing. The glucose will move this way until it is 0.5, which is half of 1, right? And 0.5 on both sides. So they will move independently of each other to equilibrate their own amounts on each side. The sucrose can't move, so it stays right where it is. All right, so then once you've done something like that, if you have more than one solute, what you're going to want to do next is take the sum of all the solutes that are now on either side, on side A and on side B, because they've done their movements, and now you need to figure out what the water is going to do in response to this. So adding up all the solutes, you get over here, I think you get 1.3 molar solutes on this side, all of them together. And over here you get 0.6 molar, right? Solutes total. Okay. So now the solvent in all this is still water, and the water will still move overall towards where most of the solutes are. So we have a higher amount of total particles over here, and the water is going to be kind of the final equilibrium creator here. So the water will move which way? Yes, the water will move this way because it's more concentrated over here, and it will be seeking to dilute that. And so B will go up and A will go down. And that explains how you would do that kind of question, okay, where you have multiple solutes, and you have to see what are the solutes going to do first. You have to pay very close attention to what the membrane is permeable and not permeable to before you make that decision, right? Because if the sucrose can't move, then you've got to leave it there. And then finally, when you've done that calculation, then you find out what the water will do. Because osmosis is still going to be needing to happen in a problem like that. Okay, I think that's it. I think that's all I was needing to explain to you. Is everybody comfortable with that? Are there any questions? I think that takes you through most of the worksheet and will cover most of the problems that you'll be faced with on that worksheet. And I have just filmed all of this, so it will be posted for you and you can look at it if you need it. Okay, thank you for your attention. I hope that was helpful.